Hello again, ladies and gentlemen. Mr. Johnny here, looking at 15.5 application of equilibrium constant problems. So first question is, how does Q compare to KEQ when it's at equilibrium? So quick question is, well, what is the difference between Q and KEQ? So KEQ is basically Q at equilibrium. So Q is pretty much just what are the products concentration over the reactants at a specific time. So it doesn't have to be at equilibrium. Q is just saying, hey, we don't know if it's at equilibrium, but here's our numbers. What would you get? What would the quotient be that you get? Whereas KEQ is saying, all right, no, this is the constant for at equilibrium. This is what it's got to be. So if it's saying, how do they compare when it's at equilibrium? They're equal to each other. Kind of a trick question, but they're equal. So the Q is for at, not necessarily equilibrium conditions. It's just, all right, here are the conditions. What do we get as our quotient? KEQ is this is what it needs to be at equilibrium. So take a look at 25. It says if Q is greater than KEQ, predict which way, forward or reverse, the equilibrium will proceed. Well, we got to remember that it's the products over the reactants, right? And you're saying that for Q, it's greater than what it should be for actual equilibrium. All right, well, if it's bigger, then we know that we have too many products. We have too many products. That's why our Q is so large. So which way would the reaction shift to get to equilibrium? Well, if we have too many products, we're going to have to shift in the reverse to use up some of them. So for example, if I had XY, X becoming Y as my equilibrium, my expressions would be, Y over X and Y over X. And it's saying that what we got right now is greater. That's ugly, huh? There we go. We have too much Y, in which case, all right, well, how do we get rid of too much Y? You shift reverse. So the reverse would be favored. 26. So at 500 Kelvin, the equilibrium constant for a reaction below is Kp equals 6.5. It says a closed container at that temperature has added to it 3 atmospheres of bromine. All right, so let's say we got 3 atmospheres of bromine, 1.5 Cl2, and 1.7 of BrCl. Based on the initial conditions, what would happen to the inside of the container? All right, well, we know Kp equals that, so we got to figure out, well, what's our Q? What's our quotient if we were to look at this initial conditions? So it's going to be products, the BrCl squared over the Br2 times Cl2. So now it's just a plug and chug. All right, so we do 1.70 squared all over 3.0 times 1.50. And what do we get? Beep, bop, boop. 0.642. All right, well, how does that compare to 0.65? Well, it's less than 0.65. Wow, right? Yeah. All right, but it's less. So what's that tell you? That tells us that we don't have enough product. We need more product to get us equal to our equilibrium constant. So which way is it going to shift? It's going to have to shift forward. Because the Q is less than. So Q less than KQ, we're going to have to go forward. Q greater than KQ, you're going to have to shift to the left. And if Q equals KEQ, you're at equilibrium. All right, 27. Equilibrium constant for the equilibrium between PCl5 and PCl3 is this value. So again, they give us the value. So that's our Kp. A sealed container initially has 0.132 of PCl5 added to it. What is the equilibrium partial pressure of Cl2? So this is going to be another one of those, hey, they said initially. So that's kind of our clue to, hey, we probably are going to have to do an icebox, an initial change equilibrium. So I'm going to draw out my icebox so that I can fill it in. So initially you got 0.132 atmospheres of PCl5. All right, this is going to be a great problem. You guys are going to love it. And that's all I start with. All right, well then how much is it going to change? Well, we know that it's going to have to shift to the right because we only have that reactant. So we're going to have to make some products. All right, well, how much are we going to make? Well, fortunate for us, the stoichiometry is real simple. Everything's 1 to 1 to 1, right? 1 to 1 to 1. All right, well, how much did it change? I don't know. I know. So let's just call that a number, that we don't know. Let's use a variable. We'll call it x. And since we started with PCl5, we're going to lose x. So how much PCl3 are we going to make? Well, we started with none, and we're going to add x to it. We're going to make x amount because of the 1 to 1 to 1 ratio. So what's our equilibrium? Well, we're going to leave it in terms of x. So for PCl5, it'd be 0.132 minus x. For PCl3, it'd be x. And for Cl2, it would be x. So now we're going to have to do some math. You guys are going to love this. It's going to be great. So we know our Kp is going to equal the products, which will be PCl3 and Cl2, all over the reactants, PCl5. All right, and we're going to plug in some of those numbers now. We got x times x all over 0.132 minus x in parentheses. And that has to equal 0.0421. All right, so now what are we going to do? I'm going to make some room. All right, so now what we're going to do is we're going to rearrange this equation so that we get it into a quadratic equation. We got x squared plus, ax plus b kind of thing going on. So we're going to have to multiply the denominator out and combine like terms and all that good stuff. So we should get x squared equals the Kp times 0.132 minus Kp times x. And what I did there was, instead of working with this ugly number, I was like, hey, I don't want to work with that ugly number. I'm going to work with Kp for a little bit because it's a little easier. So I distributed that, multiplied this across, distributed Kp. Now I want to get everything on one side equal to 0. So I get x squared minus Kp, plus Kpx to both sides, right? So we get x squared plus Kp times x, and then subtract that other part. So minus the Kp times 0.132. And that all equals 0. So Mr. Johnny, what do I do with this? Just that old school quadratic equation. If you don't have a fancy schmancy calculator that you know how to use and have it solve it for you, you're going to have to do the, x equals, I gotta even refer to it, negative b plus or minus square root of b squared minus 4ac all over 2a, where a is 1, the a is 1, the b is the Kp, and the c is the negative Kp times 0.132. So you're going to get two answers. Now you're going to be asking the question, all right, well, which one is it going to be? And that you just got to think about the problem and take the one that makes sense. So here we're talking about equilibrium partial pressure of Cl2. All right, well, we know we started with 0 and we added some stuff to it. So our value that we're going to take is going to be the one that gives us a positive value, right? So we get x equals, I wrote it down somewhere, donde está 0.0106 atmospheres. So that should be my final answer. So Again, quadratic equation, it'll come up. Remember, negative b plus or minus square root of b squared minus 4ac all over 2a. All right, hopefully you've seen that enough in math class that it carries over. If not, practice, practice, practice. All right, 28. At a given temperature, the Kp for the equilibrium below is given as that number. Sealed container is charged with 24.1 atmospheres at NO. At equilibrium, the partial pressure of N2 is blank. So this is what we're trying to solve for. All right, so it's going to be another one of those ice boxes. All right, so initially, what was the change? What was it at equilibrium? We got NO, we got N2, and we got O2. So initially, we got 24.1 atmospheres of this stuff, and we got no N2 or O2. All right, well, how much did it change? It didn't tell us, but we know. All right, well, if I started with just NO, I'm going to have to shift to the right. So I know I'm going to use up some NO. So let's call that minus X. Better yet, look at the coefficients. What's the ratio? 2 to 1 to 1. So I'm going to save myself a little bit of a headache by saying, hey, instead of calling it just X, why don't I call that 2X? Why does that save me a headache? Because now N2 and O2 I can say are just X. It's half the amount. And what happened to them? Well, we made some, so it's positive values. All right, so the equilibrium values, NO is going to be the 24.1 minus 2x. N2 is going to be x. O2 is going to be x. So we're going to have to plug that into our Kp expression. So we know that Kp equals the N2 times the O2 all over NO squared. So we got to plug in those numbers. We end up with x squared on top divided by 24.1 minus 2x in parentheses on the bottom. So now we're going to have to rearrange and put it into, a squared plus bx plus that whole setup. So we're going to, do just a little algebra, and we're going to get x squared plus 5300x minus 63865 equals 0. All right, Mr. Brownie, how did you do that? Well, I used the actual Kp value that they gave me right here, and I distributed it. So you do the algebra, you get it. This is what you should get as the expression. So now it's just the quadratic equation where x equals the negative b plus or minus square root of b squared minus 4ac all over 2a. Now, which one are you going to use? You're going to use the one that makes sense. So again, x, well, you're probably going to get a positive and negative value for x. So you're going to take the positive one. If you got two positive ones, well, then look at your initial and equilibrium for NO. If you say you had a positive, 16 as x, well, then you would end up with a negative concentration for NO, and you can't have that. So you're going to use whichever one makes sense. So no negative values for your equilibrium concentrations, and you get x equals 12.0 atmospheres. That's it. I know, horrible, right? It's just using the quadratic equation, and being thoughtful in your steps, making sure you don't make a silly mistake. One more. Given a Kp of 0.0207 at 800 K for the reaction below, during an experiment, H2 and I2 have an equilibrium partial pressure of this, respectively. What is the partial pressure of HI? This one is a much needed break from the quadratic equation. So we get Kp equals concentration. I'm sorry, we're not doing concentration, the pressure. Pressure of H2 times the pressure of I2 all over pressure of HI squared, because of that 2 right there. So now let's rearrange. What we're trying to solve for is the partial pressure of HI. All right, well, that's nice. You're right. They said equilibrium partial pressure, so we're at equilibrium. We don't have to do any of that icebox stuff. We're just solving for this. So let's rearrange. Right, and do a little algebra, do just some algebra, and I get P HI equals PH2 times PI2 all over KP square root the whole thing, right? Because this over here was for it squared. I don't want to solve for hi squared. I want to solve for hi, so I got to take the square root of everything once I move it over. So now it's a simple plug and chug. We know all those values. They gave us Kp up here, and they gave us the pressures here and here. So it's just plug and chug, and we get 4.37 atmospheres. That's it. See you in class. Bring questions.